Are here with two fundamental proofs for any student that's studying the Laplace transform. We're going to prove the Laplace transform of sine AT and cos AT, or sine omega t and cos omega t if you're in an engineering or physics application. Very often you'll see these transforms given to you in your Laplace transform table for you to remember or to apply, but not infrequently you'll be asked to derive these from first principle, which is exactly what we're going to do now. Before though, let's quickly recall the formula for the Laplace transform. We say that the Laplace transform of any function of time f of t, which we also call cap f of x, is equal to the integral between 0 and positive infinity of e to the minus st f of t dt. Perfect. So let's go ahead and immediately try to evaluate this integral with respect to sine at. Of course, we have two functions of t being multiplied by each other, so we're going to go ahead and use an integration by parts approach, where we say the integral of v du is equal to uv minus the integral of u dv. We usually pick the term or the function that differentiates to 0 to be our v, but this being an e raised to the t function and this being a trig function, we know that neither will differentiate to 0, so let's just pick e to the minus st as our v and sine at as our du. With e to the minus st being our v, of course our dv is just going to be minus se to the minus st. Du being sine at is going to make u equal to minus cos at over a. Cool. So let's rewrite this then. So uv is going to be equal to minus e to the minus st cos at over a. Let's put back our limits. Minus the integral of u dv. So u times dv is going to give us se to the minus st cos at over a dt. Wonderful. So before we go any further, let's go ahead and just fill in the limits for this one. This is going to give us e to the to the minus s infinity cos a infinity over a minus, well, since it's all over the same denominator, right, we can just make it longer, minus or plus e to the minus st, minus minus gives us plus e to the minus s 0 cos a 0 all over a. E to the minus s infinity, of course this is going to go to e 1 over e to the s infinity, which of course tends to infinity, which will give us 1 over infinity, which we know tends to 0. So this term tends to 0, which means all of this side tends to 0, which leaves us with just over here. Which is going to now give us e to the minus s times 0. Everything up here just goes to 0. E to the 0 is just 1. Cosine of a0, this just goes to the cosine of 0, and the cosine of 0 is 1. So all of this boils down to 1 over a minus, let's rewrite that a little nicer. 1 over a minus this integral here. What we can go ahead and do with this integral is just pull out this s over a to the outside, s over a, so we can rewrite the integral as, putting back our limits, should have put them here. We can rewrite our integral now as just e to the minus st cos a t. This is starting to look familiar, right? So let's go again, making e to the s minus st over v and cos at over du. So v being e to the minus st, dv will be minus se to the minus st. Let's move that off screen just for a little bit. And with du being equal to cos at, then we know that u is going to be equal to sine at over a. All right. Now, putting this all back, we now get 1 over a minus s over a, all multiplied by uv, which is just going to be e to the minus st sine at all over a, limits, minus the integral of u dv, which is going to now be minus se to the minus st sine at all over a dt. Lovely. Let's fill in these limits here. Of course, this is going to be e, wow, is going to be e to the minus s infinity sine a infinity minus e to the minus s0 sine a0 all over a. We already spoke about this, that this goes to 0, which makes all of the term go to 0. And we know that this here goes to 1. Sine a0, though, goes to sine of 0, and sine of 0 is 0, which makes this entire expression go to 0. All right, so this simplifies stuff for us, simplifies stuff. We end up with 1 over a minus s over a, all multiplied by negative. And for this integral, let's take out this negative s over a here. So this becomes plus. So we can just get rid of the sign. S over a multiplied by the integral from 0 to infinity. Let's put back the limits there as well. E to the minus st sine at dt. We have now successfully gone in a complete circle. So given that this is what we're initially trying to solve, we can rewrite this as follows. We can say that the Laplace transform of sine at, which is what we're trying to find, right, is equal to 1 over a minus, let's multiply the two of these here, s squared over a squared multiplied by, drum roll, the Laplace transform of sine at. which is really all this integral here that we've gotten back to is. Now taking it from here, we'll just move our Laplace transform sine at terms to one side. So we'll end up with here the Laplace. Let's just say, so we don't have to keep writing this, let's just let sine at equal to f of t, which means we can now write this as f of s plus s squared over a squared f of s is equal to 1 over a. Pulling this out, we get 1 plus s squared over a squared f of s is equal to 1 over a. Cool. Now, dividing both sides, we get f of s is equal to 1 over a multiplied by 1 plus s squared over a squared. Whew. Let's keep going. This is then equal now to 1 over a plus a s squared over a squared. Of course, here we'll cancel it there, and we get 1 over a plus s squared over a. Now, all we do with this is that we multiply the whole thing through by a over a, right? Which a over a we know is equal to 1. So it really doesn't change the value of the fraction by multiplying it by 1, which will then give us a over a squared plus s squared. And we've proved it. YouTube no longer, I shouldn't say no longer, doesn't yet let me upload videos longer than 15 minutes. So I'll upload the proof for cosine in the video directly after this. But that's essentially how we got from here all the way down to here. It's quite long, quite time consuming, but I hope you can see that it is not difficult to evaluate. See you in the next one.